Hello, hello. Let's talk about gradients and directional derivatives, yet another application of partial derivatives, which is just going to keep propelling us forward. So, first couple things we need to understand is a gradient is basically a vector. It's the gradient vector, okay? And the gradient vector is a vector pointing in the direction of steepest ascent. Okay, so the gradient vector is a vector that will point in the direction of like steepest slope. Let's think of it that way. To get a gradient vector, it's really just a vector made out of partial derivatives. Okay, so the gradient of f, denoted by del f, del is an upside down triangle, is equal to really df dx, comma df dy. All right, so your gradient vector is a vector whose components are the partial derivatives with respect to each of the individual independent variables. All right, so that's read as del f or grad f. And note, for each x, y in the gradient, it is a vector in the plane, not a vector in space. So if you have a 3D function, the gradient vector is a 2D vector because it's telling you what direction to go. Think of it as if you're standing on the Earth is technically a 3D surface, but we only have latitude and longitude to indicate direction. Same thing here. If I found the gradient, it would tell me what direction to head in, latitude and longitudinally, to go steepest. All right? It's actually very easy algebraically. So if I want to find the gradient of f of xy for this, and then find the gradient at the point 2, 1, I can do that. So if I want to find the gradient f of xy, I need f sub x and I need f sub y. And so f sub x is going to be a chain rule. Bring down the power, reduce it by 1, and multiply by the derivative of the inside. The derivative of 2x minus y with respect to x would be 2. So f sub x is really 2x minus y to the negative 1/2, or 1 over the square root of 2x minus y. And then if we want to find f sub y, it's going to be very similar. 1/2 2x minus y to the negative 1/2 times negative 1. So then f sub y is really going to be negative 1 over 2 root 2x minus y. So the gradient of f at any point xy is the vector 1 over root 2 x minus y, comma, negative 1 over 2 radical 2x minus y. There's f sub x, comma, f sub y. That will tell me, based on any point I could be at, what direction I should go to find the direction of steepest ascent. Okay, fine. Or I could say, you know what? If I want the gradient at the point 2, 1, I just plug in 2 for x and 1 for y. So that's going to be 4 minus 1, 4 minus 1. So the gradient of f at 2, 1 is going to be 1 over the square root of 3 and negative 1 over 2 root 3. Okay. And another thing that you sometimes want to do with a gradient vector is try to simplify it. I can come way back up here and pull out a GCF from these components of 1 over root 2x minus y, and then I'd have 1 comma negative 1/2 left over, which honestly tells me if I want to go in the direction of steepest ascent, I've got to go 1 to the right and 1/2 down to figure out the direction of steepest ascent from, honestly, pretty much anywhere. Cool. There's my gradient. Now, if you want to see what that looks like on Geogebra, which, let's be honest, who doesn't want to see what that looks like? I know I do. I am going to pull up Geogebra, and that is right here. And our function was the square root of 2x minus y, so z equals the square root of 2x minus y. So there's my function. we were at the point 2, 1, and that would be 2, 1 root 3. So there's the point that we were curious about. And if I want to go in the direction of steepest ascent, oh, look at that, I can move it. If I want to go in the direction of steepest ascent, I would have to look and say, okay, well, I'd probably need to go up like this way. And if I very carefully here, I'm going to spin this so I can see X and Y. There we go. So there's my X and my Y. It said to go in the direction of steepest ascent, I want to go +1 in the X direction and -1/2 in the Y direction. So +1 in the X direction would mean go about this way, and -1/2 in the Y direction means go like this. And if we look at that, yeah, that is where it's getting steeper. If I went like this. Cool. All right, let's do another one. So it says find the gradient of f here at the point 1, 2. Okay, well, why don't you get started while I flip my computer back over. And let's find the gradient. Gradient is really just partial derivative separated by a comma. So f sub x, let's see, is going to be y times 1 over x plus y squared. And then f sub y is, let's see, just ln x plus 2xy. So the gradient of f at any point xy is the vector y over x plus y squared, comma, ln x plus 2xy. And we want the gradient at the point 1, 2. So that's going to be, let's see, 2 over 1 plus 2 squared, comma, ln 1 plus 2 times 1 times 2. So the gradient at 1, 2, I forgot my f up here, is going to be 2 plus 4, which is 6. ln 1 is 0. 2 plus 2 times 2, which is 4. So my gradient vector is 6, 4. And let's see what this looks like, because I'm kind of curious myself. Whoops. Dropping things. Let's see. So y ln x, x plus y squared. There we go. Z equals y times ln x plus x times y squared. And so there is a very cool looking function. Ooh, I like that. That's fun. And we were supposed to be looking at this at the point, at the point 1, 2. And if I'm at the point 1, 2, my z value would be 4. So there's the point. And if we want to go in the direction of steepest ascent, it looks like I would need to, wow, everything's pretty steep from there, but this says steepest would go a little bit more in the positive x direction than you do in the y direction. That's going to be pretty hard to show here. But basically, I want to go positive x, positive y, which means kind of this way. I can't even draw it, like right there. Positive x, positive y would be like this line right here. That's a tougher one to explain. All right, so then what is the gradient? Again, it's worth repeating because it's going to come up and be important later. The gradient is the direction of steepest ascent is given by the gradient of f of x at xy, and that really is just f sub x, comma, f sub y. Fine. The gradient then leads to our need for what's called the directional derivative. The directional derivative is another vector that has a lot to do with the partial derivatives, but instead of sticking a comma between them, I'm technically going to add them together, but with some trig. Okay, so if f is a differentiable function, there we go, of x and y, then the directional derivative of f in the terms of the direction of the unit vector u equals cosine theta I plus sine theta j is d sub u of f of xy equals f sub x times cosine theta plus f sub y times sine theta. Okay, it says this definition of the directional derivative gives a unit vector in terms of its direction angle. Okay, that was a lot of words. Let's back this up a little bit. This is saying, what if you wanted to go in a certain direction, but instead of saying, I want to go in the direction of the vector 3, 2, I just said instead, I want to go 45 degrees away from horizontal, I guess. Okay, so I want to go 45 degrees with respect to the positive x-axis, or 32 degrees with respect to the positive y-axis. If I want to go in that direction, the components of the vector that'll get me there would be cosine theta, sine theta, and that would be a direction vector. Okay, one of the important things about the directional derivative is your directional derivative, no matter what form it's in, and there are multiple forms, it's always in terms of a unit vector, and I'll get to why in a second. So first thing, how do I know cosine theta, sine theta is a unit vector? Well, a unit vector is a vector of length 1, so if I can prove that this is 1 unit long, it's going to be a unit vector. So the magnitude of cos theta, sine theta would be the square root of cos squared theta plus sine squared theta. And cos squared plus sine squared is 1. So yeah, that's 1 unit long. Okay, so if I want to get the directional derivative in terms of an angle, I take the partial derivatives with respect to x and y, and I multiply them by cosine theta and sine theta. But what if I don't have an angle? What if I have a vector? Well, you can also say, wait a second, that's f sub x and f sub y as like coefficients, and there's a sum in between, and we had a vector that had an f sub x and f sub y. An alternative form of the directional derivative is the gradient dotted with u. Well, if I think about this for a second, the gradient vector is f sub x comma f sub y, and a unit vector in an angular specific direction would be cosine theta, sine theta. And when you dot two vectors, that's when you multiply and add. And I get what we had up top. Okay, so long story short, there are 2 ways to figure out a directional derivative. One way is figure out what angle you're going in, and then do the partial derivatives times the cosine and sine of that angle. Option 2, if you either don't have an angle and you just have a vector, or you do have an angle, you could also do this in dot product form. All right, so let me show you how they each work, because honestly, they're not that difficult. Find the directional derivative of this at the point 1 pi over 2 in the direction of the point 3, 4. Okay, well, wait, what does that mean? It means I'm standing at the point 1 pi over 2, and this is like my original location, and I want to walk toward the point 3, 4. Okay, so what I first have to do is say, okay, if I'm standing at one point and I want to get to another point, what direction am I going? Well, the vector that would be the direction that I'm going would be 3 minus 1, 4 minus pi over 2. I would like to head in the direction of the vector 2, 4 minus pi over 2. Okay, so I'm heading in that direction, standing on this surface. And if I want the directional derivative, okay, I want to go in the direction of a unit vector. Okay, wait, that's not a unit vector. I need to turn it into a unit vector. Well, if I want to turn that into a unit vector, I want to divide it by its magnitude. So my unit vector is going to be this thing divided by its own magnitude. Fine. So my directional derivative in the direction of that vector standing on the surface f of xy is going to be the gradient of f of xy dotted with that unit vector. Okay, So then I want the gradient vector. That's going to be the derivative with respect to x and y separately. So the derivative with respect to x would be 2x sine 2y. And the derivative with respect to y is going to be 2x squared cosine 2y. And then I want to dot that with this unit vector. Okay, I'm running out of space. I apologize. I should have given you much more space. My bad. I want this at the point 1 pi over 2. So if x equals 1 and y equals pi over 2, that's going to be 2 times 1 times sine of pi. That's 0. And then if I have x is 1 and y is pi over 2, I'm going to have 2 times 1 times the cosine of pi. So that's 2 times negative 1 is negative 2. And then I need to dot that with this. Okay. And then really when I multiply this using the dot product, 0 gets multiplied by this piece. So those really just disappear. And then I add it to whatever negative 2 times all of this is. And that's kind of a nightmare, isn't it? But let's see. I am going to do it on my calculator in my hand. So just give me a moment here. If you have a calculator, have at it. So I have negative 2, and that's being multiplied by 4 minus pi over 2. And that's all being divided by the square root of 4 minus pi over 2 squared. Except that's not supposed to be a minus, it's supposed to be a plus. My apologies. And I get 0 plus negative 1.544. So this directional derivative is negative 1.544. You gotta be honest, I didn't really like that example, so I'm gonna bake another one at the end of this. So just stick with me. I'm not thrilled with that example. Probably should have known that ahead of time, but I didn't, and I'm being honest. So there you go. All right, there's the directional derivative. Fine. Let's do another one. This one I know is better. This one says find the directional derivative of this function right here at the point 1, 2 in the direction of a vector that makes an angle of pi over 3 radians with the positive x-axis. Okay, this one's going to go better. I can promise you that. If I'm going in the direction pi over 3 radians, that means my unit vector is the vector cosine pi over 3, sine pi over 3. And that is guaranteed to be a unit vector. I don't need to divide it by its magnitude or anything. So when you are finding directional derivatives, it's great when they give you a directional derivative in terms of an angle, because the unit vector is just staring you right in the face. Now, if I want the directional derivative, I also need f sub x and f sub y, which are going to be negative 2x and negative 2y over 4, which is negative y over 2. Okay, so there's f sub x and f sub y. So the directional derivative of f of xy is going to be negative 2x, negative y over 2, dotted with cos theta sine theta. And in our case, if I want the directional derivative at the point 1, 2, when x is 1, this is negative 2. When y is 2, this is negative 1. And our unit vector is cos pi over 3 sine pi over 3. And now I'm just supposed to dot them. So I have negative 2 times the cosine of pi over 3, which is a half, minus 1 times the sine of pi over 3, which is root 3 over 2. So that's going to be negative 1 minus root 3 over 2. And that is my directional derivative. Okay, great. What is that? Well, simply put, the directional derivative gives the slope of a multivariable function at a point on the surface when moving in a given direction. Okay, so when you have that directional derivative notation, f of xy is the surface that you're on, and u is the direction that you're going. Okay, when we have f sub x and f sub y, those are partial derivatives, but those are partial derivatives if I just only move in the x direction or only move in the y direction. That gives me the rate of change of z. But we're not always just moving in an x direction or y direction. We're not just going horizontally or vertically. We're often going diagonally. And what if I wanted the slope in terms of that diagonal movement? That's what the directional derivative gives you. The directional derivative gives you the slope of something in a diagonal direction. Okay, technically in any direction. The key, though, is when you are doing the directional derivative, you must be a unit vector. Okay, has to be a unit vector. Other distinctions here. The gradient vector is a vector that points in the direction of steepest descent. We use the gradient vector either A, to find the direction of steepest descent, or B, in order to find the directional derivative. Your gradient vector is a vector. Your directional derivative is a scalar that represents rate of change or slope of z. Okay? And then last but not least, we have one more example. It says the temperature in degrees Celsius on the surface of a metal plate is that, where x and y are measured in centimeters. In what direction from that does the temperature increase most rapidly? What is the rate of increase? In what direction from 2, -3 does the temperature decrease most rapidly? What is the rate of decrease? One thing I want to say, because you're trapped here watching my video, is you might be thinking, okay, what a temperature of a metal plate? Why on earth would I have a temperature? This is actually incredibly realistic. If you think about putting like a cast iron pan over like a gas burner, where the flame hits the pan, that's going to be the hottest part where the pan is, and then the heat dissipates the further out you go. That's what this temperature function is actually showing you. Now, this isn't going to be a circular dissipation. This would be an elliptical dissipation. So if any of you have like those gas stoves where you have like an oblong heat thing in the middle of it, that would be an example of something like this. So this is a realistic, although simplistic, version, of a heat equation. All right, but I digress. It says, in what direction from 2, -3 does the temperature increase most rapidly? Well, if I want something to increase most rapidly, I want to think about the gradient vector, because that tells me the direction of steepest descent. So if I want my gradient vector, the gradient of f with respect to x, y, or in terms of x and y, would be f sub x, comma, f sub y. And if I want my gradient at the point 2, -3, plug 2 in for x, plug -3 in for y, and I should head in this direction. So if I am standing at 2, -3 and I'm very cold and I want to warm up, I should go in the direction of -16.6. Fine. What is the rate of increase? Well, the direction of steepest descent is the gradient vector. The rate of ascent is your directional derivative. So then in part B, we're basically asking, what would I have as a directional derivative at the point 2, -3 in the direction of -16.6? All right, so for my directional derivative, I'm supposed to dot the gradient vector with a unit vector. I have a vector. I don't have a unit vector. So to turn this into u, I just divide it by its own magnitude. So for part B, if I want to know how fast is the temperature increasing, if I head in the direction of the gradient vector, I'm going to dot the gradient vector with the unit vector. Okay, and so if I do that, I'm going to, let's see, when I dot these, I would get 256 plus 36 divided by 256 plus 36. Well, if I take something, that's to the first, that's to the 1/2, I really just get the square root of 256 plus 36, which is what, 292? That's how fast the temperature is increasing. And if you're thinking, I wonder if that happens every time. It does happen every time. If you ever want to find the direction of increase, if you move in the direction of the gradient vector, it's just going to be the magnitude of the gradient vector. In other words, the answer to the question, how fast would something increase if it moved in the direction of steepest ascent, would be just the magnitude of the gradient vector. Now, that's if you wanted to increase. What if you wanted to decrease? Well, if I increase most rapidly by going in the direction negative 16.6, I would decrease most rapidly by going in the direction 16, negative 6. If you negate the gradient vector, you decrease at the rate of steepest descent. And then if you wanted to find that rate of decrease, it would just be negative square root of 292. Okay, so an important note, the maximum value of the directional derivative, in other words, the steepest slope you can get, is equal to the magnitude of the gradient vector. And that's that. All right, I'm done. I'm going to give you some simple questions to do with the checkpoint that really just have to do with the formulas. So have a good day. Enjoy this comic. It is honestly one of my favorites. It's just so simple. Love it, love it. Have a great day, everybody.